Uh, some examples of crystalline solids, you can classify them into different types. You can have ionic solids, okay? Ionic crystalline solids. They're characterized by very high melting point because of ionic bonding. They're also very brittle because what happens is this. In your crystalline solid, okay, you got pluses and positive ions and negative ions right next to each other, right? If you hammer, okay, if you hit, let's say, a solid, an ionic crystal by a hammer, what happens is you shift these, let's say you were to shift this just a little bit to the right because of the force from the hammer. What happens? These negative ions could be temporarily be right next to each other, and your positive ions would be temporarily right next to each other. So that would trigger a very, very strong repulsion, and so that breaks apart your crystal. So the brittleness of ionic compounds is due to the strong interionic repulsions that would be triggered by the slight displacements that would occur if you were to hit it with a hammer. Okay? Now, molecular crystals, you can have molecules settle into a nice repeating pattern into a crystal. But generally, these crystals would have low melting point, and they have a tendency to just sublime. Okay, and the reason for that is the forces that are holding those molecules in your crystals are relatively much weaker than the forces holding the ions. You have, you have what types of forces hold molecules together in general? Intermolecular forces. So the most common one would be London dispersion forces. Those are relatively weaker compared to the ionic bonds that hold ions together. You can also have what are known as non-bonding atomic crystals. Generally, when you're dealing with noble gases at very low temperature, okay, your atoms of your noble gases are just held by very, very weak London dispersion forces. So you can have them settle into a crystal at very low temperature. So it's just a collection of atoms in a solid. That would be what you would call a non-bonding atomic crystal. You can also have metallic crystals. So metals and form metallic crystals. They have a very high melting point because of metallic bonding. What's metallic bonding? You have your nuclei, okay, of your metal. Imagine it as being buried in a sea of electrons. Okay, in a metal, remember from your periodic trends of atomic properties, your metals have very low ionization energy. Right? They don't hold on to the electrons very well. Electrons in a metal are very loosely held, so you can imagine in a metallic solid, you have these nuclei of your metals surrounded by a sea of electrons, buried in a sea of electrons that are very easily moved, that can move very easily. So that's one reason metals are good electrical conductor. Okay, so the malleability and ductility of metals has to do with the fact that atoms, the movement of your atoms, when your nuclei in your metal move, the bonds don't get broken because it's really the metallic bond is just delocalized over the entire structure. Okay, so what does malleable mean? What's a mallet? It's a hammer, right? Malleable means you can hammer them into thin sheets, so you can easily move those metal atoms so that you can spread them out into a thin sheet. Ductile means you can draw them out into a thin wire. So copper metal, you use that for your electrical wires. So your electrical wires are made up of metal, copper metal, right? Ductile means can be easily drawn out into a thin wire. Malleable means you can hammer them into thin sheets. The opposite of those things would be brittle, right? If you hammer like a salt, what happens to a salt when you hammer it? It falls apart. It's brittle. Okay. So, but you can make your metals hard and brittle by introducing irregularities within the structure, within the crystal structure. And you can do that if you were to cool your metal and then you hit it with a hammer, okay? Or you can mix different kinds of metals. So you disrupt the order in the crystalline structure. You can make your metal brittle, okay? Now, heating, if you were to heat a metal, it has a tendency to soften. Why? Because by heating it, you're giving the atoms of the metal the ability to move about. It's what's the word for it? You give them time to settle into a much better position in a way. Okay, so that's a way of removing irregularities. You can also have what are known as covalent network covalent crystals. These are crystals that are formed by atoms that form covalent bonds. So examples of these would be, the most common one would be diamond, graphene, and graphite. Let me see if I can pick up some structures from the pictures from the web for diamond crystal. Okay, let's search for images. Okay, so here's a picture of a diamond, okay, crystal. So you can see each carbon is a tetrahedral center. It's moving. All right, each carbon is a tetrahedral center. It's covalently bonded to 4 other carbon atoms. So it's a very, very strong structure, okay. Diamonds are one of the hardest materials known. It is the hardest material known, right? And you can also have graphite, okay. You can see all the atoms are covalently bonded, okay. Graphite is, you can think of graphite as actually sheets of a molecule called graphene. In graphene, you have sp2 hybridized carbon, okay. So each of these atoms here that are arranged in a hexagon are sp2 hybridized carbon atoms. So a sheet of carbon atoms forming these hexagons here is what you would call graphene, okay. And that you have layers of those to form graphite, okay. And where do you find graphite? The lead of your pencil, okay. So those sheets of carbon atoms would just slide off your pencil and attach onto your paper, right? All right. So those are some types of crystalline solids.